Welcome to EngLog, the channel where we explore software engineering, DevOps, and cloud architecture one log at a time. In today's episode, we're discussing the OpenAI research paper on why large language models hallucinate, why they sometimes produce plausible but incorrect answers, and what that means for engineers and system designers.
Welcome to the deep dive. Today, we're getting into something really important, I think, a critical challenge in AI right now. Why large language models, LLMs, sometimes just make things up confidently.
Yeah, confidently is the key word there.
Exactly. You've probably seen it, right? Those times an LLM gives an answer that sounds totally plausible, super authoritative even, but it's just wrong, completely fabricated. So we're digging into this really interesting OpenAI research paper. It kind of pulls back the curtain on why this happens, these hallucinations.
Right.
We'll look at the deep statistical reasons, but also how the way we evaluate these models might actually be making things worse.
Which is a fascinating angle.
Yeah. And this isn't just theory. Knowing this stuff is absolutely vital if you're building anything with LLM. So let's jump in.
Absolutely. And this issue, it really hits everything in AI development. Reliability, user trust, it all connects back to understanding and hopefully fixing these hallucinations.
All right.
And what I like about this paper is that it's not just hand-waving, it's rigorous. It tries to demystify what feels like this weird, almost human quirk.
Yeah, like the AI is daydreaming or something.
Exactly. But it gets down to the why at a really fundamental mathematical level. It strips away that mystery.
Okay, so let's start there. What do we actually mean by hallucination when we talk about LLMs? The paper makes a point about this, right?
Yeah, they're careful.
Yeah.
It's not like a human seeing things. It's more like generating overconfident, plausible falsehoods.
Okay.
Or, put another way, spitting out factually incorrect statements instead of just saying, I don't know. It's bluffing, basically,
Yeah.
confidently bluffing.
A confident wrong, not a hesitant, maybe. I like that framing.
Precisely. And the paper gives some almost funny, if they weren't concerning, examples.
Oh, yeah. Like what?
Well, take Adam Talman-Kalai, one of the paper's authors. They asked a top LLM for his birthday, specifically telling it, respond only if known.
Okay, seems reasonable.
He gave back 3 different dates, 0307, 1506, 0101, all completely wrong. His birthday is actually in the autumn.
Wow. So it didn't just say, I don't know, it tripled down on being wrong.
Exactly. 3 confident, different wrong answers.
Okay, what else?
Then there's the PhD dissertation thing. Different big-name LLMs, ChatGPT, DeepSeek's Llama, just completely made up titles and years for his dissertation.
And not even close, just fabricated.
Totally fabricated.
Yeah.
And my personal favorite, just because it's so simple, the intrinsic hallucinations.
Intrinsic, meaning what?
Contradicting the prompt itself.
Yeah.
They asked models like DeepSeek V3 Meta AI, Claude 3.7 Sonnet, to count the letter D in the word DeepSeek.
Okay, that's 1D. Easy enough.
You'd think. They got back answers like 2, 3, 6, even 7.
7 Ds in DeepSeek.
Yep.
Okay, yeah, that's not just a small error. That's not a typo you fix with Google.
Right.
These examples really show it's something deeper, more systemic in how these models work. Makes you wonder, if can't count letters accurately, what else is it confidently messing up?
Exactly. Which leads perfectly into the next big point from the paper.
Okay, lay it on me. Because this part, this kind of blew my mind.
Right.
The paper's first big argument, these hallucinations actually start during pre-training. And here's the real kicker. Even if the training data is perfect, spotless, error-free, How is that possible? If the input is perfect, where do the errors come from?
Well, if you connect it to the bigger picture, it boils down to the statistics of how these models learn. The paper makes this really smart link to binary classification.
Binary classification, like yes, no.
Sort of. Think about it like this. Deep down, the LLM is constantly making an implicit decision, kind of an is it valid check.
Okay.
It's deciding, is this next bit of text I'm generating likely to be valid and correct, or is it an error?
Right. It's predicting what comes next.
Exactly. And here's the math that's pretty eye-opening. The paper shows that the rate the LLM makes stuff up, its generative error rate is basically double how often it messes up that internal is it valid check.
Wait, double, so it amplifies its own uncertainty.
It's like an error multiplier baked in from the start. So if the model misjudges its own output as valid when it's not, say, just 10% of the time, that translates to a 20% hallucination rate.
Wow.
It's not really a bug you can patch. It's like an expected consequence of the math they use during pre-training, specifically minimizing something called cross-entropy loss.
Okay, cross-entropy loss. That sounds pretty technical. Can you break that down a bit for folks who might be more on the ops or architecture side?
Sure, yeah. Think of cross-entropy loss as, like, the model's grade during training. It measures how surprised the model is when it sees the correct answer in the training data.
Lower surprise is better.
Right. The goal is to minimize that surprise, to get its predictions super close to the right answers in the data. It's learning the patterns of language. Okay.
But what this paper shows is that even chasing a perfect score on that test, minimizing that loss, inherently builds in these hallucination tendencies. It's because of how it tries to approximate the sheer complexity of human language. That approximation itself introduces errors.
So trying to perfectly mimic language statistically leads it to sometimes make things up.
In a nutshell, yeah. And the paper digs into how these statistical errors pop up. They point to a few main reasons. First is what they call arbitrary fact hallucinations.
Arbitrary facts.
Yeah, this happens when there's just no solid, learnable pattern in the data for a specific fact. Researchers call it epistemic uncertainty.
Fancy term for the model just doesn't have enough good data.
Pretty much. Like, imagine you're learning about a huge city, but only one single sentence in all your training data mentions a tiny, obscure street name.
Okay.
If someone later asks you about that street, you might just confidently guess based on that one unreliable mention. You have some data, but it's flimsy.
Right. Not enough to be sure. Exactly. And the paper connects this to things like the singleton rate, how often a fact shows up only once. If, say, 20% of birthday facts in the training data are singletons, the model's basically expected to hallucinate on at least 20% of those specific facts.
Because it doesn't have corroborating evidence.
Precisely. Then there's the issue of poor models. This isn't about the data, but the model itself.
How so?
Either the type of model used just isn't good at representing a certain concept, or the specific model isn't right for the job. That letter counting example with DeepSeek is perfect here.
Ah, right, 1D.
Yeah. DeepSeek v3 struggled, but DeepSeek R1, which is built more for reasoning, apparently got it right because it could spell it out and count. It suggests R1 is just a better model for that specific task.
Different architecture, different capabilities.
Exactly. And think historically, like old school trigram models. They only looked at the previous two words. They had at least a 50% error rate on simple grammar, like out of her mind versus out of his mind, because her or his depends on something further back than two words. The model is just too simple.
So it's not always the data. Sometimes it's the limitations of the model's design, how it thinks.
Exactly right. The model's structure and its learning goals are tangled up with these error rates. And beyond those, the paper mentions a couple of other factors too,
Okay.
like computational hardness. This is when the task is just impossible, even for a super AI.
Yeah.
Think asking an LLM to break strong encryption without the key.
It literally can't figure it out.
Right. So it'll either refuse or, more likely, it'll just guess wrongly, hallucinate.
Makes sense.
Then there's distribution shift. This is super relevant for engineers using these models in the real world.
How does that work?
It's when the prompts you give the model are way different from what it saw during training. They're out of distribution.
Like asking a general chatbot for super specific legal advice it never trained on?
Exactly. You're basically pushing it outside its comfort zone, outside what it learned. That's almost asking for a confident, wrong answer.
Gotcha. And the last one?
The classic. G.I. Joe. Garbage in, garbage out.
Oh, yes.
While the paper focuses on errors even with perfect data, they acknowledge that, yeah, if the training data itself contains factual errors, the LLM will learn and repeat them confidently.
So multiple paths lead to hallucination. It's not just one thing.
Definitely not. It's a mix of the data, the model, the task, and the fundamental math of learning.
Okay, so pre-training plants the seeds. It sounds almost unavoidable statistically, but then what about post-training? You know, the fine-tuning, the alignment, all that work meant to make them better and safer. Why doesn't that get rid of these hallucinations?
That's the logical question.
And the paper has this kind of provocative take on why they stick around a socio-technical explanation. What's that about?
It's a really interesting point. If we're trying so hard to fix this in post-training, why is it still such a big problem? The paper uses this great analogy. LLMs are like students taking exams.
Okay, I can picture that.
When you're a student and you're not sure about an answer on a test, what might you do? Especially multiple choice.
Guess. Hope for the best. Maybe try to write something plausible for partial credit.
Exactly. You might guess, or even bluff, to try and maximize your score.
Right.
Well, LLMs are evaluated using similar kinds of tests, and they are optimized essentially to be good test takers.
Ah, okay. So they learn to game the test.
In a way, yes.
Mm.
The core issue the paper points to is how we score these evaluations. Most use binary 0-1 scoring.
Meaning?
1 point if you're right, 0 points if you leave it blank or say, I don't know, IDK.
Okay, I see where this is going.
Right. This setup creates a huge incentive for the model to always guess rather than admit uncertainty. Why get a definite 0 for IDK when you might get 1 point for guessing even if you're wrong?
Because there's no penalty for being wrong, just no points.
Exactly. And when models bluff, they tend to give really specific, confident-sounding answers. Remember the Kalai birthday examples, 0307, not just sometime in spring.
Right, specific guesses.
And the paper's table 2 really lays this out. It shows how most big LLM benchmarks, GPQA, MLU Pro, SWB Bench, HLE, they mostly use this binary grading. Yes, no, accuracy, pass rate. And crucially, they give 0 credit for, I don't know.
So no reward for honesty about uncertainty.
Pretty much none. Even something like Wildbench, which tries to give partial credit, still ends up scoring IDK lower than a guess that happens to have some errors. It still implicitly encourages guessing.
Wow.
And the paper states is mathematically observation 1, they call it. Under this kind of binary scoring, saying I don't know is always the worst strategy from a score maximization perspective. A model that guesses will mathematically score higher than a similar model that's honest about uncertainty.
So we're basically training our AI models to bluff. We're actively discouraging them from saying I don't know and rewarding them for just making stuff up confidently.
That's the hard truth the paper presents. It's like an epidemic, as they put it, of penalizing uncertainty.
And that reinforces the exact behavior, the confident falsehoods that we call hallucinations.
Precisely. It's a systemic incentive issue baked into how we measure success.
Okay, so this is a bit depressing. If our tests are making the problem worse, what do the authors suggest we do about it? How do we fix this epidemic?
They do propose a clear way forward. It's about changing the tests. We need to adjust the evaluation benchmarks to 1, explicitly state confidence targets, and 2, crucially, penalize incorrect answers while rewarding I don't know responses.
Okay, change the rules of the game. How would that work?
They give an example, prompt modification. Imagine telling the model something like, answer only if you are more than confident, being some threshold, like maybe 95%.
Okay.
Because mistakes get penalized 2 divided by 1 minus 2 points, correct answers get 1 point, and saying, I don't know gets 0 points.
Whoa. Okay, so there's now a cost to being wrong, and IDK becomes a safe, neutral option.
Exactly. It makes the risks and rewards clear. Guessing confidently and being wrong hurts your score. Saying IDK doesn't hurt or help, it changes the calculation for the model.
That's a huge shift. Aiming for reliably confident answers, not just any answer.
Precisely. And here's the really important part. They argue these changes shouldn't just be for some new, specialized hallucination benchmark that nobody uses.
Right, because that wouldn't change the mainstream behavior.
Exactly. These new scoring rules need to be integrated into the existing popular evaluations. Things like SWE Bench, which currently just checks if a code patch works or not binary pass-fail.
So change the big tests that everyone optimizes for.
Yes. That's how you realign the incentives where it matters most. Otherwise, the few good benchmarks get drowned out by the many that still reward bluffing.
And this ties into behavioral calibration. What's that?
Yeah, it means the model doesn't just give you a raw probability score. Instead, it figures out the most useful answer it can give while staying above that confidence threshold T. If it can't meet that threshold for any useful answer, then it says, I don't know.
So it's behaving in a calibrated way, not just reporting a number.
Exactly. There's a fundamental shift in what we ask the model to do.
Okay, this makes a lot of sense. It changes how we even define a good LLM. It's not just about fluency, but also about reliability and knowing its limits. So let's bring this back to the listener. Why is understanding all this statistical roots, the evaluation traps, why is this so vital for you as an engineer or developer, maybe just someone using these tools?
Oh, the implications are massive. First, just product reliability is huge.
Right.
Hallucinations kill the usefulness of LLM products. Think about a customer support bot giving totally wrong instructions.
Nightmare scenario.
Or a code assistant generating buggy, insecure code.
Oh.
Or a research tool spitting out fake citations. These aren't just annoyances, they're critical failures. They cost time, money, and can have serious consequences.
Definitely. What else?
Second, and maybe even bigger, user trust.
Yeah.
If users constantly get confident but wrong answers, they'll just stop trusting the AI, period. We talk a lot about building trustworthy AI, but trust requires reliability and, frankly, honesty. If the model bluffs all the time, that trust evaporates.
You learn not to rely on it.
Exactly. And third, this understanding directly impacts system design.
How so?
If you know that hallucinations are, to some extent, a predictable outcome of the statistics and the evaluation pressures, you can design your systems to handle it.
Rather than just hoping it doesn't happen.
Right. You can build in guardrails, maybe use confidence scores from the model more intelligently, design prompts that encourage caution, maybe even chain models or use verification steps. It lets you move from just reacting to errors to proactively designing for reliability.
So understanding the why lets us build better defenses.
Precisely. And ultimately, as the paper suggests, if we successfully shift these evaluations, we could end up with more nuanced language models with richer pragmatic competence.
Meaning AI that communicates better, more thoughtfully.
Yeah, more reliably, more aware of its own limits. An AI that's genuinely more helpful because it knows when not to guess. That feels like the direction we need to go.
That leads to a really interesting final thought then. If our current AI models are basically incentivized to guess to win at benchmarks, how much is that holding them back?
Interesting question.
Like, could this focus on always having an answer, even a wrong one, actually limit their ability to truly explore uncertainty, to admit limitations, maybe even to innovate in ways that require acknowledging what isn't known?
It's possible. Innovation often comes from recognizing gaps in knowledge.
Right. So could an AI that's truly calibrated, one that's comfortable saying, I don't know, or expressing nuanced confidence, could that AI actually be more intelligent, more useful in the long run than one that just optimizes for fake certainty?
It really makes you rethink what intelligence means for these systems. Is it just pattern matching and fluent generation, or does it involve knowing the limits of that knowledge?
Maybe true intelligence requires a degree of intellectual humility, even for an AI. Something to think about.
It's Tuition. Thanks for listening to EngLog. We'll be back soon with more stories and insights from the world of engineering, AI, and system design. Until next time, keep building, keep shipping.